There are two primary tasks involved in air navigation: determining your position and direction, and calculating distance, speed, time, and fuel. A number of different tools have been used over the years to accomplish these tasks. Some of them have been replaced by modern technologies, but others are still used today. Early aviators borrowed many of the navigational tools that had been developed by mariners over the centuries, such as maps, the compass, clocks, and the sextant. Here we see a very early world map from the year 1490. Do you notice which continents are missing? This is the first map that shows the Americas, made by Juan de la Cosa in the year 1500. The Bellin nautical chart, made in 1778, looks surprisingly modern in its detail of the continents. Notice the lines of latitude and longitude. Mariners utilized charts and the compass, such as the one shown here, to navigate the world's oceans. They used sextants to measure their latitude, or position north or south of the equator. Sextants determined latitude by measuring the angle between the sun and the horizon, or a star and the horizon when used at night. Measuring longitude, or the east-west distance from the prime meridian in Greenwich, England, was a bit more difficult. This required using an accurate clock which could keep track of a reference time that could then be compared with the local time. John Harrison developed such a chronometer in 1772. The first airplanes couldn't stay aloft very long or fly very far, so navigation wasn't necessary. As pilots began traveling greater distances, they borrowed from the tools which had been developed over the centuries for maritime navigation. The simplest of these tools were the map and compass. Since no aerial maps had been developed, pilots used road maps which they cut into smaller strips to make them easier to read in the cockpit. They often just followed highways or railroad tracks to get to their destination. The first airways, or highways in the sky, were developed for the air mail service. At night, bonfires were lit at airfields along the route so that pilots could find their way. These were later replaced with electrically powered light beacons. The beacons were placed on the top of a large tower next to a small shed that contained a generator to power them. To help airmail pilots navigate during the day, large concrete arrows were embedded in the ground to point the way ahead. Some of these arrows can still be seen today. Eventually, airway routes were established across the entire United States. The Army Air Corps began publishing air navigation maps in 1932. Within a few years, these were replaced by larger and more detailed sectional air navigational charts developed by the Department of Commerce. Aeronautical charts improved pilots' ability to navigate by reference to landmarks or checkpoints. This is called pilotage. Another technique, called dead reckoning, allowed pilots to navigate by means of computations based on time, airspeed, distance, and direction. Relying primarily on dead reckoning, Lindbergh was able to make landfall in Ireland within 3 miles of his intended site. The clock and the compass were the only navigation instruments installed in early aircraft like this 1917 Curtiss Jenny. Navigation became somewhat easier and safer as weather observations and forecasting improved. Weather maps such as this one were made available to pilots by the Department of Agriculture Weather Bureau. Weather balloons provided information about winds and temperatures aloft. Once the direction of the winds was known, pilots could plot their true course on an aerial chart and draw a wind triangle to determine which way to point the aircraft, the heading, to compensate for wind drift. This task was greatly simplified with the introduction of the Dalton flight computer, which would eventually evolve into the E-6B still used today. Even Mr. Spock used an E-6B to navigate on board the USS Enterprise. Now that you have some idea of how our aerial navigation techniques were developed, let's use them to plan a cross-country flight. The video that follows provides a good overview.
Before the advent of radio and satellite navigation, pilots had to know how to get from point A to point B, using only the limited resources they had at their disposal. Those resources typically consisted of a chart, a magnetic compass, a clock, and the ground below them. Using just those tools, pilots could navigate thousands of miles and arrive at their destinations on time and with little deviation from their intended route. They did this by using pilotage and dead reckoning. Even with the advanced navigation systems available today, pilots are still expected to know how to apply pilotage and dead reckoning skills anytime they fly. Navigation signals can become unreliable, equipment can malfunction, and electrical power can be lost. It's for this reason all pilots need to know how to determine their position and navigate to their destination without using anything other than a chart, a magnetic compass, a clock, and visual checkpoints. In this lesson, we will discuss how pilotage and dead reckoning work, and what you must do to successfully apply these skills in the airplane. Although the name implies it is only used by pilots, just about every person uses this technique to get from place to place. How many times has someone given you directions that sound similar to this?
What y'all want to do is follow Derby Road till you cross the railroad tracks, and then make a right at Sinclair Street. Continue till you get to the intersection where the big bank is, and then make a left onto Frontier Road. My house is the first house just past the pond on the left.
By using street names and landmarks to help you navigate your way to the destination, they are essentially providing you all of the information you need to know to find their house. This is the most basic form of navigation there is. Pilots use the same technique to get where they want to go, but from a slightly different perspective. Pilots can't read street signs, but they can still use prominent landmarks and major roads to guide them where they are going. Armed with nothing more than a VFR sectional and clear skies below, a pilot should be able to navigate to any airport of their choice. Here's how it works. Let's say you want to fly from Daytona Beach to Gainesville. With just a current Jacksonville sectional, you should be able to take off from Daytona and fly to Gainesville without any other navigational aids. On the sectional, notice that there are restricted areas between Daytona Beach and Gainesville. Instead of flying through this area, you decide to fly around it. To do that, you determine that the best course would be to fly towards Palatka-Larkin Airport and from there, head west. Keep in mind, the key to pilotage is selecting checkpoints that will be easy to see from the air. You'll also want to select checkpoints that are spaced out an appropriate distance from each other, so you can check your progress as you go. Selecting points that are too far apart could allow you to wander off course. If you are flying strictly by pilotage, you should be able to see the next checkpoint from the one preceding it. This way, you can visually transition from one point to the next as you fly along the route. Crescent Lake is a safe distance from the restricted areas, so you decide to use that as a checkpoint. Regardless of where you end up after ATC vectors you north of Daytona Beach, you will be able to see Crescent Lake and fly towards it. Following northwest along its eastern shoreline, you can pick up the tributary of the St. Johns River that feeds into the northernmost part of the lake. Following the tributary to where it joins the St. Johns River will put you due south of Palatka-Larkin Airport. You should have no problem seeing the airport from that position. From there, you can pick up State Road 20 that travels west towards Gainesville. Following that road will eventually bring you to Noonan Lake, 5 miles southeast of Gainesville Regional. Although the course we chose was not as direct a route as possible, with only the help of a VFR sectional, it did serve its purpose and allowed us to navigate from point A to point B without getting lost. This type of navigation is as basic as it gets. Aviation, however, is never content with good enough, and pilotage alone is not enough to get us to our destination in the safest, most efficient, and reliable way possible. That is where Dead Reckoning comes in. Combining pilotage and dead reckoning gives a pilot a way of knowing where they are and where they are going, and just as important, when they will get there. Dead reckoning provides the key component of time to the equation. Knowing how long it will take us to get somewhere is extremely important for a pilot, because an airplane only has so much before it runs out of fuel. Another bonus of using dead reckoning is that we can increase the precision of the course we fly. By planning our course in advance, we can fly more direct routes, which in turn allows us to get to our destination in a more fuel-efficient and faster manner. It also lets us know if something isn't going as planned, and could give us an early indication of a potential problem. So, what exactly is dead reckoning? Dead reckoning is the process of estimating your position by advancing a known position using course, speed, time, and distance traveled. In other words, if you know the course and the speed you are traveling, and then take your time over a certain checkpoint, you should be able to estimate your arrival time at your next checkpoint. All you need to know is the distance to that point. It also allows you to compare your pre-flight performance calculations to your actual in-flight performance. If you calculated that your ground speed would be 120 knots, but your dead reckoning shows that you are only going 100 knots, well, then you know something is different than what you planned for. Or, if you calculate that a particular heading, flown at the speed you are traveling, will have you arriving at your next checkpoint in 15 minutes, but find that it only took 13 minutes to get there, then you know the wind speed has changed from what you planned for. Dead reckoning will also let you know whether the heading you are flying is correct for the route you plan to travel. Your position in relation to the checkpoint can also provide more information about the wind. If you arrived at your checkpoint and find yourself left of course, then there is a good likelihood that the wind has shifted from what was forecast and requires a change of heading to hold your course. Using this new information will enable you to make a more accurate time estimate to your next checkpoint and allow you to better compensate for the wind. One other advantage of using dead reckoning for navigation purposes is that it will assist you in your pilotage tasks. It's not always easy to find prominent landmarks that you can see clearly from a great distance. By using dead reckoning, you have an estimate of when you will arrive at the next checkpoint, so you know when you should be looking closely for your point. When flying cross countries at Embry-Riddle, you will always use a navigation log. The nav log is designed to allow you to input your pre-flight planning for the flight, along with all of the checkpoints you plan on using. The performance calculations you come up with prior to the flight will provide estimated ground speeds and headings to fly to reach each checkpoint. Once in the air, you will use the nav log to verify your performance and modify your planned headings and power settings as necessary. The nav log requires the use of both pilotage and dead reckoning. You will use pilotage to keep track of where you are, and you will use dead reckoning to better estimate when you will get to where you are going. When used together, pilotage and dead reckoning allow you to fly your route as safely and efficiently as possible, and will keep you thinking ahead of the airplane.
The first tool we'll need is a sectional aeronautical chart. These charts cover the entire United States. Large metropolitan areas that lie within the boundaries of a sectional chart often have an additional terminal area chart with a zoomed-in view. This is indicated by the small magenta squares dispersed across the map in this slide. The sectional charts show airports and airspace along with various other topographical features. For our flight planning, we'll be using the Los Angeles sectional chart. We'll also need a plotter. Data from the winds and temperatures aloft table can be found on aviationweather.gov. We'll use an E6B flight computer to make our calculations. Then we'll record the results on a flight planning sheet like the one shown here. So let's get started. We'll plan a flight from John Wayne Airport to Borrego Valley, which has the identifier L08. There's a great Italian restaurant right on the airport, so that will be a good excuse to make the flight. The first step is to use our plotter to draw a straight line between the two airports. It's a good idea to use a pencil first to make sure the course line is drawn properly, then go over it with a highlighter so you'll be able to see it well in the cockpit. A yellow highlighter is not recommended, as this color is used all over the sectional chart to designate a populated area. Bright pink works very well. Following the line of longitude up to the scale at the top of the protractor, read the true course of 108 degrees at the top. Next we'll find the isogonic line closest to our course. It's 12 degrees east, which means we'll subtract 12 degrees from our true course of 108 degrees. To help you remember when to add or subtract the magnetic variation, use the phrase, west is best and east is least. Just to review, lines of longitude run north and south from the North Pole to the South Pole. However, magnetic north is slightly different from true north. Isogonic lines are drawn on sectional charts to show how much variation there is between true north and magnetic north. Easterly variation is subtracted and westerly variation is added. We also need to determine an appropriate cruising altitude. We should fly at least 2,000 feet over mountainous terrain to avoid turbulence and downdrafts produced by wind as it blows over the mountain tops. The maximum elevation figure for the quadrant we will be flying through shows that the highest obstacle within the quadrant is 6,900 feet. Our course line also crosses a mountain peak that is 6,533 feet high. Between 0 and 179 degrees, aircraft flying under visual flight rules, VFR, must fly at odd altitudes plus 500 feet, and between 180 and 359 degrees they must fly at even altitudes plus 500 feet. Since we will be flying on an easterly heading of 108 degrees, we will need to fly at an odd altitude plus 500 feet. Adding in 2,000 feet to stay well above the mountains, we choose a flight altitude of 9,500 feet. We'll use the ruler edge of our plotter again to measure the distance between John Wayne Airport and Borrego Springs Airport. It's 81 nautical miles. Then we'll circle prominent visual checkpoints spaced evenly along the route and measure the distance between them. During the flight, we'll refer to these checkpoints to make sure we're on course. To maintain our course, we'll also need to factor in a wind correction angle. First, we'll go to aviationweather.gov and look at the winds and temperatures aloft table. We see that the wind at 9,000 feet is 310 degrees at 18 knots and at 12,000 feet it's 310 degrees at 26 knots, so the wind at 9,500 feet is 310 degrees at approximately 19 knots. It increases 1.3 knots for each 500 feet above 9,000 feet. Now that we have the wind direction and speed for our planned flight altitude, we can use the E6B flight computer to calculate the wind correction angle. We set the wind direction of 310 degrees under the true index at the top. We then use the slide to place the grommet under any number. We'll choose 100 to make our calculation easier. We count up 19 lines from 100 and make a wind dot that corresponds to the wind speed of 19 knots. We then rotate the disk to set our true course of 108 degrees under the true index. Then we adjust the slide to place the wind dot at the 85 knot arc, which represents our true airspeed in our climb out from John Wayne Airport. Now it's all set. The flight computer does the rest of the work. We read the ground speed of 102 knots under the grommet and the wind correction angle of 5 degrees left under the wind dot. To determine our cruising ground speed and wind correction angle, we adjust the slide again, placing the wind dot on the 120 knot line that represents our true airspeed in cruise. We don't rotate the disk because our true course of 108 degrees does not change. Under the grommet, we read our ground speed of 137 knots. Under the wind dot, we see that our wind correction angle is 4 degrees left. Now we can start filling in the information on our flight planner sheet. First, we fill in all of the checkpoints we circled on the chart. The true course, altitude, wind direction and speed, and temperature are all the same for each row. In the first row, we fill in the planned true airspeed of 85 knots and the wind correction of 5 degrees. We subtract this number from our true course of 108 degrees, then subtract the magnetic variation of 12 degrees to get a magnetic heading of 91 degrees. Because of interference from avionics equipment installed in the instrument panel, most aircraft compasses are slightly off in their readings. This is called deviation. The amount of deviation is recorded on a small card placed next to the compass. To obtain the actual compass heading to use in flight, pilots will need to check the compass card and add in the amount of deviation to the magnetic heading. To keep things simple, we'll just assume a deviation of 0 degrees for this aircraft. We move over to the next columns and fill in the compass heading, distance to the first checkpoint, distance remaining, and ground speed. We then fill in the information for the remaining rows, using our cruising airspeed of 120 knots and wind correction angle of 4 degrees. Now we'll need to use the E6B flight computer to calculate the time and fuel required to reach the first checkpoint at Lake Elsinore. We line up the 60, representing 60 minutes, on the inner wheel, with our ground speed of 102 knots. Zeros can be added as needed to the numbers on the scale to obtain the number we need to work with. For example, in the picture we have lined up the 60 with the second hatch mark past the 10. This could represent the number 12, but since we need to line up 102 knots per hour, we just add a 0 to the 10. This may seem confusing at first, but with a little practice it becomes easy. Looking at the outer scale, we find the number 25, which corresponds to the 25 nautical miles to the first checkpoint at Lake Elsinore. Since we have already set the speed to 102 knots per hour, we just find the number closest to 25 on the scale of the inner wheel. It's about 15, close enough. So it will take 15 minutes to fly the 25 nautical miles from John Wayne Airport to Lake Elsinore if our ground speed is 102 knots per hour. Returning to the flight planner sheet, we fill in the 15 minutes under ETE, estimated time en route. Since we plan to depart KSNA at 1900 Zulu, we should arrive at the checkpoint at 1915 Zulu. We fill this in under ETA, estimated time of arrival. Now let's calculate how much fuel we will burn during those 15 minutes. We know from previous flights, and checking the airplane flight manual, that we will burn about 10 gallons per hour in cruise. It would actually be a few gallons more than that in the climb, but to keep things simple for this exercise, we'll keep it at 10. We rotate the inner wheel of the E6B and place the 60 under the 10 to represent 10 gallons per hour. Looking over at the 15-minute mark, we see that it lines up with 25. Obviously, this can't mean 25 gallons in 15 minutes, so we move the decimal over from 25.0 and make it 2.5 gallons in 15 minutes. That makes sense. Returning to the flight planner sheet, we fill in 2.5 under fuel used. Assuming we will start off with 40 gallons of fuel, there will be 37.5 gallons remaining. Now that you've seen how to use the E6B flight computer, see if you can fill out the rest of the rows and columns on the flight planner sheet. For the FAA commercial pilot written test, you'll be allowed to bring a plotter and an E6B flight computer, either the mechanical or the electronic version. The link at the top of the page provides a site where you can take free FAA practice tests.